Thank you very much, Mr. Chairman. Good afternoon, everyone. This is about other extreme. We got an excited talk about extreme temperature, and now we talk about extreme light intensity. Can we use concentrated sunlight for acceleration of degradation? And this is example of collaboration of our group with Hall Center and Dr. Yulia Gallagher. So, with just some history, we start our work on study with inverted solar cells produced in RISO, in Frederick Krebs group. And I show you one example of this, and before just tell you about our system. It's a parabolic mirror. I'm sorry. How is it going on? This one? Yes. It's parabolic mirror which tracks the sun outside. And we have a piece of iris which can control the indoor light from 0 to 1 sun. And this parabolic mirror concentrates light on a flat mirror which redirects light to fiber which goes indoor. And the cell is, if you want a uniform illumination of the cell, we put a kaleidoscope. It's quartz kaleidoscope for uniform enough illumination. And for 1 millimeter fiber, we can achieve 10,000 suns on the exit. We can also control temperature, or we think that control temperature. I will talk about it. And if we just put on this inverted geometry just 5 suns for 1 hour, and you see what's 100 minutes in this case, what was the results? You can see short circuit current, VOC, fill factor and efficiency as a function of light intensity. We usually, first of all, we measured PV performance also not with solar simulator, but with sunlight. I didn't mention it, but maybe on our cost meeting I will talk about it in more details. That in Sdebaker at noontime, plus minus 2-3 hours, we have a mass 1.5 global spectrum. Not only this, we have also a huge ratio between direct and diffuse light, so we can concentrate sunlight because physics forbids to concentrate diffuse light. So you can see short circuit current, light intensity of short circuit current before and after such illumination is nothing changed. It's a very small intensity, and it means that nothing changed in photo generation in the active layer, but strong degradation at VOC at lower intensities that the previous speaker told us this is a very characteristic behavior for generation shunting in the samples, and also characteristic for shunting behavior for fill factor. And as a result, we have the same degradation of efficiency. So we measured also dark IV and got the direct confirmation of the shunting. And because it was observed only on zinc oxide containing cells, we decided that this is the well-known behavior of zinc oxide layer, and if it is, it should be reversible. And it is reversible. You can see that at 20 minutes rest, just reverse DAC IV and also VOC, light intensity of VOC. But even more interesting that if we do this 2 seconds of 20 volts in reverse biased, it has a very nice and very sharp recovery, and even better than for so-called fresh cells. So we decided that we can also do this for so-called fresh samples, and we really have a huge improvement in performance just by this very simple reverse biased procedure. So actually, it was 2010. This was our first paper of concentrated sunlight, also done with Frederick Krebs samples. And you can see that if we put 60 suns, and immediately the temperature was about 55 Celsius, and this was 3 hours of such exposure, it's a huge degradation. It's a 2 times degradation of short circuit current, very strong degradation of VOC, actually stronger than logarithm of short circuit current, so it's additional degradation of VOC, and fill factor go to its minimum 0.25 value. So when we try to cool the cell, we see that the degradation is not so crucial. It's a small degradation in all parameters. So we decided for that time, we were very optimistic that, okay, we can separate the light-induced mechanism of degradation and the temperature-induced mechanism of degradation. So we can do many things with such methods. And Frederick today in the morning showed us their beautiful concentrators with sunlight and with solar simulator. They published a paper in Advanced Energy Materials last year showing a very interesting result. But this result shows that we all guys who wants to do this study with a solar concentrator have a huge problem. The problem, okay, not problem, challenge. The problem is that this is the result, what they study. It was a study of non-encapsulated just P3HT, and they measured degradation. And if you see, if you measured it one sun, it one light, and then they increase it for 50 suns, 100 suns, 150 suns, and put it as a function not of time of intensity, but in the dose in suns hours. So if everything is linear, it should be the same curve, but it's not. It's a huge difference. The most simple answer, what is the problem? The problem is the temperature, because the temperature is different. And this is a very big problem in any kind of concentrated sunlight, that the temperature, if you put a lot of light intensity, you have different, we couldn't even measure temperature correctly because it's a huge gradient. So the aim of our study was to suggest something, to develop a new method for, our aim is to do it for 5,000 suns. Again, if you see this, it's about, the maximum was 150 suns. But we want to use a very high concentration with independent control of light intensity and sample temperature in the accelerated degradation test. So for this, we use another completely different system without the fiber, and the system is the following. We have a, oh, I'm sorry, again, didn't get a lesson. The system is the following. There is outside, there is a flat heliostat with track the sun, and send the parallel lines of light to laboratory, to the window. Here there is another flat mirror which redirected to more or less big parabolic mirror. In the focus we have 15,000 suns. But here we have a lot of space. There is no fiber, everything is open. So we can chop, what we do, we chop the sunlight. We switch off and switch on natural sunlight very fastly. Here we put our kaleidoscope and we can do so. We developed this system for, you can see how it works, yeah? For study of temperature coefficient of concentrated sun, inorganic triple junction concentrated solar cells. We do a lot of works for this. And you see that it's a similar VOC of the function of time like a previous speaker showed us. We measure it up to 6,000 suns. But what this curve is important. If this is the time when we open the cell by a chopper, yeah? And then we close the cell. But if this is a horizontal, what does it mean? It means that there is no overheating of the cell during the illumination. So we can be sure about it. Then this chopping system, we have the same light concentration of sunlight, but the entire power will be strongly less. And in this kind of this geometry of chopper, it's less about by factor of 20, 18 actually. And this is our time characteristics. So we use host cells with this zinc oxide and even titanium oxide free cells with this hexagonal structure of contacts. We already study, we do some PV characterization as a function of light intensity of these cells and published it in 2011, again with Yulia and her colleagues. And this P3HT PCBM it was a very good encapsulated, and just to show how good it is, I can show you. But let's talk first about the temperature. The temperature, if we put this kaleidoscope, we can irradiate one hexagon. And what we did, in the dark, we cooled the cell either to 5 degrees or to 25 degrees. And start to measure what's happening under the sun. And if we do just continuous irradiation, we can either put, for example, 500 suns, 1 hour, you see what's the result. We just burn the cell. So it's a huge increase of temperature. So what we did, we want to do two things. First of all, we start to cut the infrared irradiation, which doesn't work with organic PV anyway. And the second one, we use this chirping. And you see that this is continuous irradiation. This is continuous irradiation. This is infrared cutting, and the best result is for chirping. You see that almost no increase in temperature. And for example, when we use this 100 suns kaleidoscope, we have increase only for less than 1 degree. This is continuous illumination, and this is chirping. And if we use a very small kaleidoscope, we can go to 5,000 suns with increasing of only 20 Celsius. So we first study the degradation of just encapsulated blends, P3ST, PCBM blends, and measure UV visible absorption. And what we first demonstrated that this is in terms of photo bleaching, it's a very extremely stable stuff. So our best results is without chirping, this is the most strong dose. It's for 300 suns, and you see that almost no photo bleaching on polymers and a small degradation in PCBM part. But this dose is equivalent to even to Sdebaker in a very, very strong environment to more than 1.6 years of outdoor illumination. So we also do it with chirping, but of course with smaller dose, but with high concentration, with about 2,000 suns and about 5,000 suns, and you see similar trends. No degradation of polymer and small degradation on PCBM part. So this is a very optimistic result, but when we start to measure solar cells, the result is completely opposite. It's a very strong degradation. So what we see is, this is 145 suns. It's a maximum concentration we can irradiate this big, I didn't say this is a 2 by 2 square centimeter samples, we can irradiate it uniformly. So what you can see, that as produced cell, it's this green line, and then after 1 hour of exposure of these 145 suns, you see the degradation. And you see more degraded to 2 suns and 3 suns. And what we see, this is a characteristic result of increasing of series resistance of the cell. Just from the book. You increase the series resistance. It was a hypothesis, speculation. But this speculation confirmed by the measurement of external quantum efficiency. That when you measure external quantum efficiency, you get the same result. No degradation at all. How it's possible? 2 times degradation of short-circuit current and no degradation of external quantum efficiency. The explanation that there is no degradation of photocurrent, it's just the effect of series resistance. Because external quantum efficiency, this was measured without light bias. If we do it with light bias, you see the strong degradation. And this degradation pronounced if we increase the intensity of light bias. We increase the photocurrent and series resistance losses. This is no light bias, 0.5 sun, 1 sun, and 2 suns. And I should say that for S-grown sample, there is no such, it was the same result. It's not effect of light biases. So this you can see for the most strongly degraded sample for 300 suns, it's a huge effect of with light bias, and also you can see that this is a very, very strong effect, also sublinear behavior of photocurrent. So our colleague from Tokyo showed us today. But most interesting results, we also can superlinear behavior of photocurrent of some stages on degradation. What does it mean? That photocurrent increase with light intensity superlinearly. It's a characteristic behavior for traps. It's also known in amorphous silicon for material, any solar cells with a lot of traps. You can see this, the dose is not so strong, or a very high concentration, And you can see that external quantum efficiency for S produced after 7 minutes of such irradiation, after 11 minutes of such irradiation. You see the degradation. Small degradation in polymer part and most degradation in fullerene part. This is a measurement of power as a function of our monochromatic light as a function of voltages on the lamp. So you can see that when we increase voltages, we increase power. And you see that here you have a superlinear behavior. As we increase power of monochromatic light, we have a stronger, and this effect is mostly in the absorption of fullerenes. And the same when we also put a light bias, you have increasing effect. So this what we decide that on this stage of degradation, we generate traps, and this shows the superlinear behavior of photocarbon. You see that it shows that this is exactly in a part of PCBM absorption. So it's traps in a fullerene moiety of the device. So our conclusion that we suggest an experimental approach for using highly concentrated sunlight with an independent control of light intensity and sample temperature in the accelerated testing that may select light-induced mechanism in the OPV degradation from those controlled just by the cell temperature. This technique is good for screening of new materials, comparing, let's say, qualitatively at least. And we are open to study different materials. We already started to work with perovskite cells, and tomorrow you are invited for our poster. I think it's poster number 8 about the study, the similar study for perovskite materials. Experiment with encapsulated PCBM P3ST blends under sunlight concentration up to 5,000 suns and dose up to 3,600 sun-hour reveals no P3ST photo bleaching and slight degradation in fullerene absorption. However, the corresponding treatment of the cells results in significant degradation of their external quantum efficiency and degradation and power conversion efficiency and degradation of charge collection and generation of traps in PCBM channel of the device were suggested as underlying mechanism for sub and superlinear dependence of photocurrent on light intensity, respectively. And our message for measurements of, and today it's under discussion how to measure correctly external quantum efficiency at short circuit current. Our message to the community is that you should be very careful about it. It's not only sublinear behavior, it can be superlinear behavior, and it's strongly dependent on the stage of degradation, different materials and different degradation stage. And thank you very much for your attention.
Let me start off. So it's quite clear that you see most degradation in the C60 part, and you attribute this to possible traps. Did you also investigate further with infrared to see maybe if there's dimerization or other reasons?
Yes, we are trying to do. I didn't show it. We use Raman and also Fourier transform infrared study. The problem is that it's a distinguish between what we will discuss on cost is to do it, you should open the field. And unfortunately, with the Hall center, it's impossible that this kind of encapsulation, we couldn't open it. We did it for our own encapsulation, but it should be done on separate on the certain encapsulation mechanism. Yes, it's. I think it's a dimerization process. If you look in general, in this particular case, we don't know. We didn't open it because of the special, let's say, secret encapsulation developed by Hall Center.
I see a question at the back. Could you please wait? Could you please bigger? Let's wait.
I thought it would be fine. How much faster can you then do these degradation experiments compared to one sun illumination without the day
This is a big question. The question about acceleration factors. It can be huge. If you see this curves published by Frederick Krebs in Advanced Energy Materials last year, they conclude about 200 or even more. And it can be faster. But the problem is that we don't understand it. It's non-linear. And we are very far to say that we can predict what's happening at one sun. I would say that even study with ULA cells, because at one sun, it's outdoor. We already discussed it today in the morning, that at one sun, it's another environmental factor involved. For example, in our place, first of all, it's much more UV. We cut a bit UV. The second one, it's a huge difference in temperature in the desert conditions, in night and day. It's accumulation of water. And this is the first step. The second step, okay, we should do the detailed study comparing with one sun. And also we can, if we really check the temperature constant, we can also, one of the open question is, what's control the photo-induced degradation? Dose or just light intensity? This is also a question should be addressed. But we are ready to start this, these studies. We are going to do it. But it should be addressed to certain material and certain device architecture, certain donor-acceptor paths. It depends.
Okay. If there are no more questions, let's continue with the flash presentation. But let's first thank Eugene again.